Testing, can you hear me? Hello. Okay, so this stream I'm going to be reading operating systems again. Hold on. Right. Let me just change to full screen. Right. So in the operating system book, I read about network file system. This time I'm going to be reading this chapter called Anti file system. No idea what that is. I just extend this. Okay. The Andy file system was introduced at Carnegie Mellon University in the 1980s, led by well-known professor M. Satyanarayanan of Carnegie Mellon University, Satya for short. The main goal of this project was simple: scale. Specifically, how can one design a distributed file system such that a server can support as many clients as possible? Interestingly, there are numerous aspects of design and implementation that affect scalability. Most important is the design of the protocol between clients and server. In NFS, for example, the protocol forces clients to check with the server periodically to determine if the cache contents have changed. Because each check uses server resources, frequent checks like this will limit the number of clients a server can respond to, thus limit scalability. AFS also differs from NFS in that from the beginning, reasonable user visible behavior was a first class concern. In NFS, cache consistency is hard to describe because it depends directly on low level implementation details, including client side cache timeout intervals. In AFS, cache consistency is simple and readily understood. When the file is open, a client will generally receive the latest consistent copy from the server. So AFS version 1. We'll discuss two versions. The first version, which we will call AFS version 1, but actually the original system was called ITC Distributed File System, had some of the basic design in place but didn't scale as desired, which led to a redesign in the final protocol, which is version 2. One of the basic tenets of all versions of AFS is whole file caching on local disk of the client machine that is accessing a file. When you open a file, the entire file, if it exists, is fetched from the server and stored in a file on your local disk. Subsequent application read and write operations are redirected to the local file system where the file is stored. Thus, these operations require no network communication and are fast. Finally, upon close, the file is flushed back to the server. Note the obvious contrast with NFS, which caches blocks, not whole files, although NFS could, of course, cache every block of an entire file and do so in client memory. Let's get into the details a bit more. When a client application first calls open, the AFS client side code, which the AFS designers call Venus, would send a fetch protocol message to the server. Do they have a diagram somewhere? So the client Forget that. There's a bulb over there. I was just testing some things. So the client sends a message to the server using open client side code is what fetch would send a fetch protocol message to the server. The fetch protocol message would pass the entire path name of the desired file. So we have fetch pro, uh, protocol, and then server sends file. What? Server sends file path, and then the file server, the group of which they call vice. Fetch protocol message would pass the entire path name of the desired file to the file server. The group of this protocol, it includes file path. We have Venus and we have Vice, which would then traverse the path name, find the desired file, and ship the entire file back to the client. Client side code would then catch the file on the local disk of the client. And then send file. Oh, we can write on the thing. Never mind. Send file and then cache file. Cache file on local disk. The client side code would then cache the file on the local disk of the client. As we said above, the subsequent read and write system calls are strictly local in AFS. They are redirected to the local copy of the file because the read and write calls act just like calls to the local file system. Once a block is accessed, it may be cached in client memory. Okay, so as we said above, subsequent read and write system calls are strictly local in AFS. No communication with the server occurs. Right? Read and writes are now local. Just redirected to a local copy of the file because the read and write calls act just like calls to a local file system. Once a block is accessed, it may be cached in client memory. Thus, AFS also uses client memory to cache copies of blocks that it has in its local disk. Also, cache local blocks. Finally, when finished, the AFS client checks if the file has been modified. If so, it flushes the new version back to the server with the store protocol message sending the entire file and path name to the server for permanent storage. If I modified, send new version to server. We have fetch protocol and store protocol. Store protocol. The next time the file is accessed, AFS version 1 does so much more efficiently. Specifically, the client side code first contacts the server using the test auth protocol message in order to determine whether the file has changed. If not, the client would use locally cached copy, thus improving performance by avoiding a network transfer. So next time the file is accessed. So now basically file needs to, to be accessed again. Then that means test auth protocol to check test auth protocol, determine whether the file has changed. Check whether file changed. I should do it downwards. If not, the client would use locally cached copy, thus improving performance by avoiding a network transfer. If file not changed, use local copy. The figure above shows some of the protocol messages in AFS version 1. Note that this early version of the protocol only cached file contents directories. Only cached file contents. Directories, for example, were only kept at the server. Test auth, test whether a file has changed. Test auth sounds like whether a user has access to the file or not. Get file stat, fetch, store, set file stat, and list directories. One of our advisors, David Patterson, used to encourage us to measure a system, demonstrate a problem before building a new system to fix that problem. By using experimental evidence rather than gut instinct, you can turn the process of system building into more scientific endeavor. Doing so also has the fringe benefit of making you think about how exactly to measure the system before your improved version is developed. When you do finally get around to building the new system, two things are better as a result. First, you have evidence that shows you are solving a real problem. Second, you now have a way to measure your new system in place to show that it actually improves upon the state of the art. And thus, we call this Patterson's law. Problems with the version 1. A few key problems with this version of AFS motivated the designers to rethink their file system. To study the problems in detail, the designers of AFS spent a great deal of time measuring their existing protocol to find out what was wrong. Such experimentation is a good thing because measurement is the key to understanding how systems work and how to improve them. Obtaining concrete good data is thus a necessary part of the system construction. In their study, the authors found two main problems with AFS version 1. Part traversals costs are too high. When performing a fetch or store protocol request, the client passes the entire path name to the server. Server, in order to access the file, must perform a full path name traversal, first looking in the root directory to find home, then in home to find Ramsey, and so forth, all the way down until finally the desired file is located, with many clients accessing the server at once. The designers of AFS found that the server was spending too much of its CPU time simply walking down directory paths. A client issues too many test auth protocol messages, much like NFS and its overabundance of get attribute protocol messages. AFS version 1 generated a large amount of traffic to check whether a local file was valid, uh, to check whether a local file was valid with the test auth protocol message. The server spent much of their time telling clients whether it was okay to use their cache copies of a file. Most of the time, the answer was that the file had not changed. There were actually two other problems with AFS version 1. Load was not balanced across servers, and the server used a single distinct process per client, thus including context switching and other overheads. The load imbalance problem was solved by introducing volumes which an administrator could move across servers by balance load. The context switch problem was solved in AFS version 2 by building the server with threads instead of processes. However, for the sake of space, we focus here on the main two protocol problems above that limited the scale of the system. So improving the protocol, the two problems above limited the scalability of AFS. The server CPU became a bottleneck of the system, and each server could only service 20 clients without becoming overloaded. Servers were receiving too many test auth messages, and when they received fetch or store messages, uh, were spending too much time traversing the directory hierarchy. Thus, the AFS designers were faced with a problem. How should one redesign the protocol to minimize the number of server interactions? So version 2 introduced the notion of a callback to reduce the number of client-server interactions. A callback is simply a promise from the server to the client that the server will inform the client ca- when a file that the client is caching has been modified. By adding this state to the system, the client no longer needs to contact the server to find out if a cached file is valid otherwise. Rather, it assumes that the file is valid until the server tells it otherwise. Notice the analogy of polling versus interprets. AFS version 2 also introduced the notion of a file identifier similar to the NFS file handler. Instead of path names to specify which file a client was interested a, an FID in AFS consists of a volume identifier, a file identifier, and a unifier. To enable reuse of the volume and file IDs when a file is deleted. Thus, instead of spending whole path names to the server and letting the server walk the path name to find the desired file, the client would walk the path name one piece at a time, caching the results and thus hopefully reducing the load on the server. For example, if a client accessed the file home ramsey notes.txt and home was the AFS directory mounted onto root, so this root was the local root. Okay. Client would first fetch the directory contents of home, put them in a local disk cache, and set up a callback on home. Then the client would fetch the directory Ramsey, put it in a local disk cache, and set up a callback on Ramsey. Finally, the client would fetch notes.txt, cache this regular file in the local disk, set up a callback, and finally return a file descriptor to the calling application. See figure 50.2 for a summary. fd open home ramsey notes.txt, send fetch home file identifier Ramsey, receive fetch request, look for Ramsey in home directory, set up callback on Ramsey, return Ramsey's content. Receive fetch reply, write Ramsey to local disk cache, record callback status of Ramsey, send fetch to node.txt, receive fetch request, look for node.txt in Ramsey, the setup callback on notes.txt, return notes.txt's content, receive fetch reply, write notes.txt to local disk, disk cache, record callback status of notes.txt, local open of cached notes.txt, return file descriptor to application. So read performs a local read, close to local close. If file has changed, fetch to server. And then next time we open a callback directory valid, we use the local copy. And when we use notes.txt, we also use the local copy. The key difference, however, from NFS is that with each fetch of a directory or file, the AFS would establish a callback with the server, thus ensuring that the server would notify the client of the change in its cached state. The benefit is obvious, although the first access to home remc notes.txt generates many client server messages. It also establishes callbacks for all the directories as well as the file notes.txt. And thus subsequent accesses are entirely local and require no server interaction at all. When discussing distributed file systems, much is made of the cache consistency of the file systems provide. Cache consistency the file systems provide. However, this baseline consistency does not solve all problems with regards to file access from multiple clients. For example, if you are building a code repository with multiple clients performing check-ins and checkouts of code, you can't simply rely on the underlying file system to do all the work for you. Rather, you have to use explicit file level locking in order to ensure that the right thing happens when such concurrent accesses take place. Indeed, any application that truly takes care of concurrent updates will add extra machinery to handle conflicts. The baseline consistency described in this chapter and previous one are useful primarily for casual usage. When a user logs into a different client, they expect some reasonable version of their files to show up there. Expecting more of these protocols is setting yourself up for failure, disappointment, and TFL frustration. When we discussed NFS, there are two aspects of cache consistency we considered: update visibility and cache staleness. With update visibility, the question is when will the server be updated with a new version of a file? With cache staleness, the question is once the server has a new version, how long before the client see the new version instead of an older cached copy? Because of callbacks and whole file caching, the cache consistency provided by AFS is easy to describe and understand. There are two important cases to consider: consistency between processes on different machines and consistency between processes on the same machine. Between different machines, AFS makes updates visible at the server and invalidates cache copies at the exact same time, which is when the updated file is closed. A client opens the file and then writes to it. When it is finally closed, the new file is fetched to the server. At this point, the server then breaks callbacks for any clients with cache copies. The break is accomplished by contacting each client and informing that the callback it has on the file is no longer valid. This step ensures that clients will no longer read stale copies of the file. Subsequent opens on those clients will require a refetch of the new version of the file from the server. Okay, hold on a minute. AFS makes update visible at the server, validates cache copies at the exact same time. Okay, let's see. AFS makes an exception to this simple model between processes on the same machine. In this case, writes to a file are immediately visible to other local processes. Process does not have to wait until a file is closed to see its latest updates. This makes using a single machine behave exactly as you would expect, as this behavior is based upon typical Unix semantics. Only when switching to a different machine would you be able to detect a more general AFS consistency mechanism. One, there is one interesting cross machine case that is worthy of further discussion, specifically in the rare case that processors on different machines are modifying a file at the same time. AFS naturally employs what is known as a last writer wins approach, which perhaps should be called last closer wins. Specifically, whenever whichever client calls close last will update the entire file on the server and thus will be the winning file. The file that remains on the server for others to see. The result is a file that was generated in its entirety either by one client or the other. Now, the difference from a block based protocol like NFS, in NFS, writes of individual blocks may be flushed out to the server as each client is updating the file, and thus the final file on the server could end up as a mix of updates from both clients. In many cases, such a mixed file output would not make much sense. Imagine a JPEG image getting modified by two clients and pieces. The resulting mix of writes would not likely constitute a valid JPEG. Timeline showing a few of these different scenarios can be seen in figure 50.3. The columns show the behavior of two processes, P1 and P2 on client 1 and its cache state. One process on client 2 and its cache state and the server, all operating on a single file called imaginatively F. For the server, the figure simply shows the contents of the file after the operation on the left has completed. Read through it. Okay. Client 1, P1, P2 cache, P3 cache, and server disk. So open file. So file created, write file, um, and then close, and it's stored in the cache. Hold on, I just need to do something. I'll get back in a few minutes. Okay, never mind. So file is created on client 1, written and then closed, and it's stored in client 1. File is opened again. Oh, and then it's stored at disk, right? Server disk. And now client open, read, close, and then nothing happened. Now open, we have written B, and then the process 2 opens file, reads B, and then closes. Now client 2 opens F, but it's reading local processes see writes immediately, remote processes do not see writes. So it reads A when it should be B. So open file, read A, close. So when client 1 closes the file, B is now stored at server disk. So remote processes do not see writes until close has taken place. Open, read, close. Now it's reading B, which is correct. Okay, now open F, but process 1 has also opened F and written a new thing called D, but client 2 has written C to it. So client 2 closes first, so C is written to disk, and client 1 closes second, now D is written to disk. Unfortunately for P3, the last writer wins. All right. From the description above, you might sense that the cache recovery is more involved than with NFS. You would be right. For example, imagine there is a short period of time where a server S is not able to contact a client. For example, the C1 is rebooting. While C1 is not available, S may have tried to send it one or more callback recall messages. For example, imagine C1 had file F cached on its local disk and then C2 updated F, thus causing S to send messages to all clients caching the file to remove it from their local caches. Because C1 may miss those critical messages when it is rebooting upon rejoining the system, C1 should treat all of its cache contents as suspect. Thus, upon the next access to file F, C1 should first ask the server whether its cached copy of file F is still valid. If so, C1 can use it. If not, C1 should fetch the newer version from the server. Server recovery after a crash is more complicated. The problem that arises is that callbacks are kept in memory. Thus, when a server reboots, it has no idea when the client memory has which file. Thus, upon server restart, each client of the server must realize that the server has crashed and treat all their cache contents as suspect. And as above, we establish the validity of a file before using it. Thus, a server crash is a big event, as one must ensure that each client is aware of the crash in a timely manner or risk a client accessing a stale file. There are many ways to implement such recovery, for example, by having the server send a message saying don't trust your cache contents to each client when it is up and running again, or by having clients check that the server is alive periodically with a heartbeat message, as it is called. As you can see, there is a cost to building a more scalable, sensible caching model with NFS. Clients hardly noticed a server crash. All right. Scale and performance of AFS version 2. With the new protocol in place, version 2 was measured and found to be much more scalable than the original version. Indeed, each server could support about 50 clients. Further benefit was that client-side performance often quite came close to local performance because in the common case, all file accesses were local. File reads usually went to the local disk cache. Only when a client created a new file or wrote to an existing one was there need to send a store message to the server and thus updating the file with new contents. Let us also gain some perspective on AFS performance by comparing common file system access scenarios with NFS. In the figure, we examine typical read and write patterns analytically. Small file, sequential read, AFS divided by NFS, so 1111. So for large file, twice as fast. For large file, single write, 2 times NL. What is N? It is N. Small files have NS blocks in them. Medium files have NM blocks. Large files have NL blocks. We assume that small and medium files fit into memory of a client. Large files fit on a local disk, but not in client memory. We also assume for the sake of analysis that an access across the network to the remote file for the file block takes in L net time units. Access to local memory takes LM, LMEM. Okay. And access to local disk takes LDisk. The general assumption is that the net time unit to the remote server for a file block is more than the local disk, which is more than local memory. Finally, we assume that the first access to a file does not hit in any cache. Subsequent file accesses, we assume, will hit in caches if the relevant cache has enough capacity to hold the file. The columns of the figure show the time a particular operation roughly takes on either NFS or AFS. Okay. First, in many cases, the performance of each system is roughly equivalent. For example, okay, For example, when first reading a file, the time to fetch the file from the remote server dominates and is similar in both systems. You might think AFS would be slower in this case as it has to write the file to local disk. However, those writes are buffered by the local file system cache and thus set costs are likely hidden. Similarly, you might think that AFS reads more from the local cache copy would be slower, again because AFS stores the cache copy on disk. However, AFS again benefits here from local file system caching. Reads on AFS would likely hit in the client-side memory cache and performance would be similar to NFS. Second, an interesting difference arises during a large file sequential reread. Because AFS has a large local disk cache, it will access the file from there when the file is accessed again. NFS, in contrast, only can cache blocks in client memory. As a result, if a large file is reread, the NFS client would have to refetch the entire file from the remote server. Thus, AFS was faster than NFS, in this case by a factor of LNet divided by NDisk, assuming the remote access is indeed slower than local disk. We also know that NFS in this case increases overload, which has an impact on scale as well. Third, we know that sequential writes should perform similarly on both systems. AFS in this case will write the file to the local cache copy when the file is closed. The AFS client will force the writes to the server as per the protocol. All right. Yeah, I'll just skip to the next part. Overall, we see that NFS and AFS make different assumptions and not surprisingly realize different performance outcomes as a result. One challenge of evaluating any system is the choice of workload. Because computer systems are used in so many different ways, there are a large variety of workloads to choose from. How should the storage system designer decide which workloads are important in order to make reasonable design decisions? The designers of AFS, given their experience in measuring how file systems were used, made certain workload assumptions. In particular, they assumed that most files were not frequently shared and and accessed sequentially in their entirety. All right. Given those assumptions, the AFS design makes perfect sense. However, these assumptions are not always correct. For example, imagine an application that appends information periodically to a log. These little log writes, which add small amounts of data to an existing large file, are quite problematic for AFS. Many other difficult workloads exist as well, random updates in a transaction database. Like we saw with the introduction of Berkeley FFS, the designers of AFS took the opportunity when building their system to add a number of features that made the system easier to use and manage. For example, AFS provides a global namespace to clients, thus ensuring that all files were named the same way on all client machines. NFS contrast allows each client to merge NFS servers in any way that they please. AFS also takes security seriously and incorporates mechanisms to authenticate users and ensure that a set of files could be kept private if a user so decide. NFS, in contrast, had quite primitive support for security for many years. AFS also includes facilities for flexible user-managed access control. Thus, when using AFS, a user has a great deal of control over who exactly can access which file. NFS, like most Unix file systems, has much less support for this type of sharing. Finally, as mentioned above, AFS adds tools to enable simpler management of servers for the administrators of the system. Summary: AFS shows us how distributed file systems can be built quite differently than what we saw with NFS. The protocol design of AFS is particularly important by minimizing server interaction. Each server can support many clients and thus reduce the number of servers needed to manage a particular site. Many other features, including a single namespace, security, and access control list, make AFS quite nice to use. The consistency model provided by AFS is simple to understand and reason about, and does not lead to the occasional weird behavior as one sometimes observes in NFS. Perhaps unfortunately, AFS is likely to on the decline because NFS became an open standard. Many different vendors supported it, and along with CIFS, the Windows based distributed file system protocol, NFS dominates the workspace. Although one still sees AFS installations from time to time, the only lasting influence will likely be from ideas of AFS rather than the actual system itself. Indeed, version 4 now adds server state and thus bears an increasing similarity to the basic AFS protocol. Yeah, I will read the summary and then I will end the stream. Well, that was too quick in my opinion, Professor. Yes, distributed systems are complicated and cool and well worth your study, not in this book. Student, that's too bad. I want to learn more. Professor, like what? Student, well, everything can fail. Professor, good start. By student, but by having lots of these things, you can hide much of the failure that arises. Professor, keep going. Student, some basic techniques like retrying are really useful. Professor, that's true. Student, and you have to think carefully about protocols, the exact bits that are exchanged between machines. Protocols can affect everything, including how systems respond to failure and how scalable they are. Professor, you really are getting better at this learning stuff. Student, thanks. Okay. And you're not a bad teacher yourself. Professor will thank you very much too. Student, so is this the end of the book? Professor, I'm not sure. They don't tell me anything. Student, me neither. Let's get out of here. Professor, okay, student, go ahead. Professor, no, after you. Professor, please. Professor's first. Professor, no, please, after you. Student, exasperated, fine. Professor, so why haven't you left? Student, I don't know how it turns out. The only thing I can do is participate in these dialogues. Professor, me too. And now you have learned our final lesson. There's also a security section over here. I'm going to be reading this section too. All right, I will end the stream here. And yeah, I'll see you guys next stream, whenever that would be. Anyways, see you next time then. Bye.